Okay, so good afternoon, all. So I welcome you all once again to this afternoon scientific session. So in this afternoon session, we have three number of speakers and one special talk. So to be held by Professor Somak. So to begin this afternoon scientific session, Hmm. Yeah. So sorry for interruption due to connections here. So may I call upon Dr. Mumul Dibi so to take over these sessions here?
Thank you. Uh, am I
Thank you,
audible?
Mumul. Yes, yes, you're
Okay,
audible.
so good afternoon, everyone, and welcome to the final scientific session of NEMA-VII. So we have three speakers in this session, as well as followed by a special lecture. So the first presenter of this session is Dr. Sanjeev Kalita from Guwahati University, and he will be speaking on astrophysical and cosmological tests of gravity. So the time for the presentation is 45 minutes, so tentatively about 40 minutes for the presentation and 5 minutes for interaction. So over to you, Dr. Kalita.
Thank you, Dr. Munmoon. Am I audible to everyone?
Yes.
Fine. Then I'll directly start. I am once again delighted to be part of NEMA-VII, and I'm grateful to all the organizing committee members for giving me opportunity to present some of my recent findings in this meeting. My topic is on astrophysical and cosmological taste of gravity, and the talk from reference number 3 to 7 independently carried out by me and with my PhD students on astrophysical test of gravitational theories near the galactic center black hole. I will review some of the tests of gravitational theories near the galactic center black hole, as well as in cosmology. And then I'll proceed for the some of the recent findings that we have realized on how much we have understood about gravity near the supermassive black hole sitting at the top of gravity, that means on large scale, or the accelerated expansion may be a result of negative pressure fluid or negative pressure field. So still we are unable to distinguish between these two, and this is a major goal of upcoming observations to be carried out by dark energy survey and Euclid mission. And strong field regime, we have many tests going on, particularly in binary pulsars, and gravitational waves, and the galactic center black hole, where the gravitational potential is much, much larger than the potential we started near the solar system. The strong field test is important because we want to test the metric and the quantum corrections near the black holes, and we also want to test black hole theorems. Then we want to extract gravitational physics in high curvature regime, particularly shows shadow observations like Event Horizon telescopes have done, and also near binary pulsars. The upcoming square kilometer array is going to have a lot of taste of gravity near binary pulsars, and is a strong field taste. When we talk about taste of gravity beyond the solar system, I mean beyond which field limit or static field limit, we have two potential laboratories to test gravitational theories. One is the galactic center black hole, where the potential is 10 to the power minus 4 in the unit of c square, and that is 100 times solar magnitude. And the currently observed region near the S stars, near the black hole, has proved this kind of region. In pulsars and stellar mass black hole, the potential is running from 0.1 to nearly 1. And this is something like 100,000 times greater than the solar system environment. And these tests are really going on to understand how space-time behaves in strong field regime. We go by Karl Popper in this meeting. In science, we never prove a theory, rather we try to falsify alternatives to the one. Something is happening whether black hole theorems are correct or the parameters are correct, for example, mass, spin, and charge. And that will prove whether the no-hair theorem is correct, for example. This is a particular case. Then we are eligible to test gravitational theories, particularly scalar tensor theories, or FR theory of gravity, or higher dimensional theory of gravity, simply by measuring the Paris-Sector shift. We can constrain all those of beautiful alternatives to general relativity, mathematically consistent alternatives and very serious alternatives so far as cosmology is concerned. Very recently, in 2020 to 2022, several papers have been released to test dark energy interaction near the galactic center black hole, because scalar tensor theory of gravity is eligible for explaining accelerated expansion of the universe, and also they have large implications for the large-scale structure formations. So galactic center black hole is independent laboratory to constrain all those alternatives to ZR, which we are invoking impact on our understanding of gravity. Then about probing gravity, how far we have probed gravity. This is the environment. In gravitational waves like LIGO events, they probe potential of the order of 1 unity in the logarithmic unit. The potential by c square is nearly 1, because we are probing almost close to the singularity. Next to gravitational wave comes the S stars moving near the galactic center black hole. And one of the most studied star near the galactic center black hole is S2 or SO2. And the potential is something like 10 to the power minus 4 in the unit of c square. In the log unit, this is minus 4. So therefore, I have picked up the galactic center black hole as an independent laboratory which can complement all the tests that have been done by gravitational waves. And we need independent tests, of course, in science if we want to really do precision science, particularly. So this large potential is also required, also large mass, because finally this is desirable for cosmological aspects. In case of gravitational waves, the objects are very small. So even though the potential is very large, the objects are small. The mass scale is small. So if we probe supermassive black holes, that in addition to testing gravity, that will be interesting for cosmological aspects also, because the supermassive black holes are cosmological objects. They formed in the primordial universe in dark matter halo. So testing gravity will definitely say something about the other problems in cosmology also. We have 3 eyes on the galactic center black hole. One is the Keck telescope, UCLA Galactic Center Group, led by Andrea Gage. Then we have VLT, this is Max Planck Group, Reinhard Genzel. And we have recently realized Event Horizon Telescope, which is going to stare at the galactic center after NEMA-VII black hole. Particularly, VLT has done a great job because many times. And this gravity interferometer is going to go beyond S2's orbit theory. And several theoretical works have been done on this. And people have constrained Yukawa gravity, particularly the Keck group, is it all 2017, by observing S8 orbits. These are 2 stars, very compact orbits. And the coupling parameter and the range of Yukawa gravity have been constrained in 2017. Then people also have been able to constrain massive gravity. That means constraining the graviton mass. Observation of S2's orbit, it has given graviton mass in the future to find out this FSP independently and to see how the Schwarzschild precision behaves. Does it tally with GR or it shows some kind of violation? Then test of modified gravity has been also been carried out. This one. Sorry for inconvenience.
Just share it again.
Is it visible now?
Yes. Could you make it full screen?
Let me see this. Is it visible?
Yeah, it is visible, but it's not in the presentation mode. So, okay. Okay, then please go ahead.
Has it changed?
No.
No. Okay. Then
It is still stuck on slide 8.
slide, yeah. The test of gravity near Sagittarius there, right?
Yeah.
Okay. The test of modified gravity and extended theory of gravity, particularly from pericenter shift of S2. And one of the theories which has been mostly studied is the FR gravity. We call scalar-on gravity because it contains a scalar mode. And Kaluza-Klein gravity, and these 2 theories of gravity have been recently tested by our group. And some kind of focus has been made to see how to constrain these kind of theories with upcoming facilities, such as VLT and the 30-meter telescope is coming. So these are some of the existing tests and some of the expectations that we are going to have to test gravity near the galactic center black hole. We will talk particularly for scalar gravity. The upper gravity is given by this action. It's a free function f of Ricci scalar, and it has a scalar field psi and a scalar mass m psi. And in my model, the upper gravity comes from curvature correction to vacuum fluctuation near the black hole. And the scalar field and scalar mass has been computed, and it comes out to be 10 to the power minus 16 electron volt. And the scalar field is something like 1000. Exactly, I am giving the number. And the coupling parameter, the scalar gravity is looking like Yukawa gravity, and the coupling parameter comes out to be 10 to the power minus 4. And one of the methods that I have used in order to calculate these parameters is that I linearize the scalar dynamics equation, scalar field equation near the black hole, and try to see the coupling parameter. And the vacuum fluctuation that I am considering near the black hole is containing two scales. One is UV scale, one is the IR scale. The UV scale of the fluctuation has been taken to be the event horizon of the black hole, and the IR scale is coming from the wavelength corresponding to the Hawking temperature of the black hole. And these two scales are giving me scalar mass and finally the scalar coupling in dimensionless form. And one of the beauty of this scalar gravity is that it gets screened. It's called screen gravity. If the mass of the scalar is very large and the coupling parameter is very small, then gravity almost behaves like Newtonian in strong field value. If the mass of the scalar is very low compared to 10 to the power minus 16 electron volt, then the coupling parameter is high, then the gravity becomes unscreened. It leaks out to larger scales. So I will discuss the effect of screen gravity and unscreened gravity here and try to see how they affect the pericenter shift. And this kind of investigation had been reported in 2018 and 2020 by me independently, and that has been a working model to test scalar gravity for the first time near the galactic center black hole. So I have categorized two types of scalars. One is called massive and cold scalaron. The mass of the scalaron is larger than thermal energy of the Hawking temperature, corresponding to Hawking temperature, and that is 10 to the power minus 18. And my scalaron is massive compared to KBT Hawking, that is 10 to the power minus 16 electron volt. Then there are low mass scalarons, as has been reported by the Cake group in 2017, Heath et al. And this is the scalaron mass is less than KBT, that is far, far below 10 to the power minus 18 electron volt. So I have categorized it to two. Then I have Kaluza-Klein gravity. The higher dimensional black holes, of course, are important. The stability of the bound orbits have been discussed by Dadish et al. Long back, and there are many works in subsequent years how to test higher dimensional gravity by observing the shadow of the black holes. And this is a probe for theories beyond ZR, of course. It is a regime of quantum gravity. One of the astrophysical aspects of higher dimensional gravity is that it predicts power law potential, and hence it may give rise to some kind of testable effects through the pericenter shift. In our work, we have Kaluza-Klein 5-dimensional degrees of freedom, and that degree of freedom is the 5-dimensional Planck mass, MPL5. And many authors are trying to say that the 5-dimensional Planck mass may behave as cold dark matter. I mean, that is something like 1000 ZeV or more than 1000 ZeV. But there is no direct test in cosmological scale of such proposal. And for the first time, it has been reported that near the galactic center, probably we can constrain this kind of model independently and try to say whether these kind of models really work in cosmology. So there are two aspects. The pericenter shift in Kaluza-Klein gravity with a potential 1 by r squared is different from Newton. And then we are trying to find out the allowed range of the 5-dimensional Planck mass through available bound on the PPN parameters beta and gamma. Next, given the astrometric capability of existing and upcoming facilities, such like VLT, Cake, and TMT-like facilities, can we give some bound on the 5-dimensional Planck mass? I should say lower bound because it should not come below 1000 ZeV, because 1000 ZeV this supersymmetry scale, and below 1000 ZeV we have this electroic scale coming. So definitely Planck mass has to lie above supersymmetric scale. So we have to give some lower bound. We are sourcing for breaking point of general relativity near the black hole as independent test. That is the first two panels. These are unscreened gravity. I am trying to make full screen. Dr. Devi, it is visible?
It is visible, but it is not full screen yet, like not in the presentation mode.
Okay,
Yeah.
but I don't know.
But if it is a technical problem, then please go ahead like this only.
Correct. Fine. These the two panels, the first panel and the middle panel, it is showing two graphs. The pericenter shift in the y-axis and x-axis is the semi-major axis of the stellar orbits. And 10 to the power minus 21 and 10 to the power minus 20 electron volt. We can see that if the scalaron mass is 10 to the power minus 21 electron volt, it is far below 10 to the power minus 18. So it is lying in the in the hot scalaron. The gravity become unscreened. That means the pericenter shift becomes larger towards the larger scale. But if we go to higher, the larger mass, say 10 to the power minus 20 electron volt, we see that the pericenter shift start dominating towards the smaller scale for the scalaron. If we go to larger stellar orbits, the pericenter shift dies out. And this is, I have plotted for two eccentricities. One is E 0.5, the first panel, and the middle panel eccentricity 0.9. We see the same effect. The low mass scalarons becomes dominating in the larger orbits. But if we go to high mass scalaron, then the pericenter shift becomes large towards the smaller or compact orbits. So this is why I call it as unscreened gravity. And if we look into my scalarons like 10 to the power minus 16 electron volt, and these the field amplitude 1217, that corresponds to coupling 10 to the power minus 4. Let me say that this coupling and field amplitude, they are inversely related in my model. And for two eccentricities, I see that the effect of the scalaron becomes dominating towards extremely compact orbits, something like 10 AU or 20 AU. 10 AU and 20 AU near the galactic center black hole, we should not expect any stars. But we are expecting pulsars moving near the black hole, and SKA is going to have some kind of promise for observing these pulsars moving near the galactic center black hole at just the small orbits. There is another detector called black hole cam that is also going to observe the pulsars moving near the galactic center black hole in orbit as small as 10 to the power as small as 10 to 20 AU. This is one of the stars to have unscreened and screened gravity. And this is our recent work, 2022. It has been reported, and now it is in press for FPJ. And again, I try to make full screen, but I don't know why it is not working. We see the dotted line is the pericenter shift for the modified gravity, scalaron, of course. And I have plotted again for the cold scalaron and the hot scalaron, 10 to the power minus 17, 10 to the power minus 19 electron volt, and for two different kind of coupling. One is psi naught field amplitude 0.33 that was reported by Keck group in 2017. And in this case, it is the theoretical amplitude 1217, that is our work. And the left hand side is particularly these these two panels are for psi naught equal to 0.33. And that gives rise to very, very large coupling. If the coupling is very large, and irrespective of the scalar mass, we see that we can see some breaking point. The solid line is general relativity pericenter shift, and the dotted line is modified gravity pericenter shift. So we see the intersection point that I call as a breaking point. And again, we see that we can see breaking point near, say, 100 AU or 1000 AU. 1000 AU is something like S2's orbit. The most studied star is the S2's orbit. So that is something like 1000 AU or 990 AU. We can see some breaking point. That is for hot scalaron, 10 to the power minus 21 electron volt. But if you come to the right panel, what we see, irrespective of whether it is a hot scalaron or the cold scalaron, the modified gravity is well suppressed by general relativity. If we see the dotted line is below the general relativity line. And these kind of scalarons are dominating towards extremely larger scales, which is beyond the interest of the stellar orbits. It will go to the galactic outskirt. That will be important for cosmological discussion. So this is one of the findings for unscreened gravity, which are very, very small coupling. Then investigation of black hole spin. This has been proposed long back that spinning black hole can support scalar hair, and scalaron is a scalar hair. And it was reported long back, around two years back, that spinning black hole, both sub-Kerr and super-Kerr, can support scalaron with mass less than 10 to the power minus 18 electron volt. So this was our task to investigate the spin values for which the spin effect and the quadruple effect on the pericenter shift becomes comparable to the scaleron effect. That means I want to maximize the scaleron effect, just making it equal to the pericenter shift coming from spin-induced effect and quadruple-induced effect, and try to see whether the spin can be calculated from such scaleron masses. And these tables are showing all those spin values chi. Say this is for A equal to 74 AU. I get spin values 0.91, 0.69, 0.75, and 500 AU, 100 AU, 990 AU. Up to S2's orbit I am going. And that is for E equal to zero 0.9 and E equal to 0.1. Very low eccentricity and very high eccentricity. So we see that spin up to 1 can be estimated by different scalerons. It's all the low mass scaleron and high mass scaleron, both of them are present. So this is an independent opportunity by seeing the scaleron-induced effect equal to the spin-induced effect, and we can estimate the spin of the black hole. Now the question is, these kind of spins are something like the Kerr black holes. So for example, you can go to 0.980, then 0.690, we have 0.1, very low spin, 0.85. So it's a very beautiful spin values we can estimate. And this one of these issues of observation is that we have to constrain the spin of the black hole if we want to test the no-hair theorem or scalar hair effect. It is effect of scalar hair. So this was an independent opportunity to relate spin of the black hole with scaleron mass. Coming to Kaluza-Klein gravity, that the pericenter shift in 5-dimensional Kaluza-Klein gravity was calculated, and with, of course, with the power law potential 1 by r squared. And by equating pericenter shift with the pericenter shift for any parameterized modified gravity theories given by parameter gamma beta, it was equated, and we are trying to find out what is the allowed range of these 5-dimensional Planck mass. I am not displaying the complicated formula for pericenter shift for Kaluza-Klein gravity, and that is a complicated equation involving the Bessel functions and the mass of the black hole, the eccentricity of the orbit, and the semi-major axis of the orbit. Gamma beta are the PPN parameters. The available bound on the PPN parameters in galactic center environment was reported in 2020, both by gravity collaboration and others. These are the bounds. And with these bounds, we were trying to find out the allowed range of the 5-dimensional Planck mass. And keeping beta fixed, we were plotting the 5-dimensional Planck mass with respect to gamma value. Then by keeping gamma fixed, we were trying to plot with respect to beta value. This was the 5-dimensional Planck mass plotted. And we see in both the cases that the 5-dimensional Planck mass is not lying very far from the supersymmetric scale, and that is 1000 ZeV. If I read from this graph, then the 5-dimensional Planck mass is something like 10 to the power 4 ZeV. This is allowed ranges. That is, numerically, this was computed. But this allowed range does not go beyond 10 to the power 4 ZeV. And that is a very poor constraint because the PPN parameters that is important for constraining 5-dimensional Planck mass through this equation is very poorly constrained in the galactic center environment. If I say poorly constrained, because we have seen in the last more than 2 decades the gamma beta parameters, how precisely they have been constrained in the solar system environment, and compared to solar system constraint, these are very, very poor constraint. So therefore, we are trying to give a focus to astrometric uncertainties of VLT gravity and then K and TMT like ELTs that is upcoming. So the pericenter shift in Kaluza-Klein gravity, this upper bound we are equating to 2 sigma, where sigma is the astrometric uncertainties of this the VLT, K and TMT, and then are trying to find out the lower bound on the 5-dimensional Planck masses. If I see these different semi-major axes starting from 45 AU up to say S2 like semi-major axis 1000 AU, now we see that these upcoming facilities are eligible to see Kaluza-Klein mass up to 10 to the power 6 ZeV. That is a little bit far away from the earlier allowed range. Is the lower bound is little bit elevated. It is up to 10 to the power 6 to 10 to the power 7 ZeV. So these kind of Kaluza-Klein particles, if they are constituting cold dark matter,
I can't hear the speaker. What about others?
Here also we can't.
Yeah, maybe some network issue at his end.
Yes,
Yeah, let us just wait for some time.
yes.
they will be strongly constrained, at least up.
He has left. That's
No,
he.
he has joined again. So, Dr. Kulita, can you hear us?
Yes, yes. Now we can see. It's coming out.
Am I audible?
Now, yes. We
Yeah.
actually lost it for some time, but now,
Yeah.
yes.
Yeah. Fine. Fine. What I was trying to deliver is the through the pericenter shift in Kaluza-Klein gravity equating to 2 sigma of these upcoming astrometric facilities, we can see that these facilities like cake, for example, cake has astrometric uncertainty of 0.16 milliarc second. Then gravity detector on BLT, it is something like 0.03 milliarc second. 30-meter telescope-like facilities will carry astrometric uncertainty 0.015 milliarc second. With these facilities, the pericenter measurement of the compact stellar orbits will be able to constrain Kaluza-Klein mass or five-dimensional Planck mass around 10 to the power 6 to 10 to the power 7 GeV. So this is the first report which tells that many beautiful theories of physics, fundamental physics, which is important for cosmological issues, can be constrained by the pericenter shift of compact stellar orbits with the upcoming facilities. I have the following remarks based on these astrophysical tests near the galactic center black hole. So this is a very potential laboratory to constrain FR gravity and higher dimensional gravity. And the upcoming observations of say VLT and cake and also this event horizon telescope that is going to observe the galactic center shadow will be eligible to say something about or constrain these modified gravity or rule out if possible. Then scalaron gravity is heavily screened for cold scalaron. In my model, it is 10 to the power minus 16 electron volt. But they get unscreened for hot scalaron and they will have impact on cosmological scale. So that is my future prospect of these scalarons. And these tests are extremely important for cosmology, as I said. And this is expected, this kind of test, separation or shift of the stellar orbit is expected to be independent opportunity because it is going to complement other tests like event horizon shadow measurement and the M87 black hole after they are going to carry forward to Sagittarius A star. Future prospects lies in binary pulsars and cosmological scales. In case of binary pulsars, the post-Keplerian parameters I said, this is the pericenter shift is one of the parameters, this post-Keplerian parameters, and there are other four. It will have noticeable effect on the post-Keplerian parameters, and gravitational wave, of course, carries a lot of potential to constrain the post-Keplerian parameters, which are sensitive to particular theories of gravity. In case of cosmology, there are two issues, and I will conclude with that. If I have FR gravity and that is unscreened scalaron, it will affect the dynamics of the dwarf galaxies. And that was reported by some authors in 2011. Because FR gravity can give rise to enhanced attractive force, scalaron force. It is something like Yukawa attractive force. The scalaron force will affect. If it is unscreened, it will go towards larger scales. I have shown in my diagram. The low mass scalaron and high coupling, it is called unscreened. It will affect the H1 disk and the dark matter part of the dwarf galaxies. However, the stellar disk of the dwarf galaxies will be unaffected because in much more compact scale, these scalярons are screened and they are affecting only the large scale dynamics of the system. Therefore, you will get a distortion of the galaxy because the stellar disk is unaffected and the outer periphery of the galaxy is affected by the scalaron force, and it will give a noticeable effect, that is distortion of the dwarf galaxy. So this is one independent test in cosmological scale about the upper gravity. Then large scale structure is also heavily affected by scalaron, and I am just showing you one simulation done by Lee, that was 2012. The smaller field amplitude psi naught or larger coupling, it gives rise to concentration of matter and enlarged void. So this is the parameter which is in my model it is called psi naught, and they are writing f r naught because psi is first derivative of the f function with respect to Ricci scalar. And if we decrease, for example, if we decrease f r naught, I mean if we decrease psi naught, that means we are increasing the coupling. Then we see that the concentration of the matter is going high, and this void, this triangular shaped low density region is the void. If we go to lower fr naught value, that means I am increasing the coupling of these scalaron, then the void become larger and the concentration of matter become also large. The concentration become large. The galaxy clusters will become highly clumpy and the void become less dense. So these are implication of scalarons, and starting from the galactic center, now we are trying to extend up to cosmological scale. How the galactic center permitted the scalaron field amplitude is going to have impact on cosmological discussion of these structures. With this, I conclude, and I am again thankful to the organizers and for all the audience. I'm thankful for being my audience. This was my report of the recent work on modified gravity and how to test it with galactic center black hole and how we can carry forward to cosmological scale. Thank you very much.
Thank you, Dr. Kalita, for the detailed and informative presentation on your excellent work. So now it is open for interactions. So if you have any questions, you can just unmute yourself and take part in the interactions. I don't see any questions yet.
Yeah, this is.
Yeah, so I just had a small question. Like, I mean, what are the upcoming experiments, like large scale experiments, which I mean you can actually expect that some hints can come from the experimental?
See, Euclid mission is upcoming to test gravity on cosmological scale. That is, we are expecting something from the Euclid mission.
Okay.
And then this dark energy survey is studying this clumpiness of dark matter part. And as I have shown in the last the simulated image, this clumpiness will be sensitive to FR gravity or general relativity, whatever it is. So whatever theory of gravity modifying we are considering, that may be constrained by the large scale structure, the clumping observations. And in cosmological scale, it is very important.
Okay. Also, there are some lab-based dark energy experiments, like just proposed experiments, but I'm not sure if they can actually provide hints on this kind of large-scale. I mean, where you need hints from large-scale structures also. Those might not be sufficient, I guess.
Yeah, because see the scalaron field, they at least it doesn't come to lab scale. It goes to say galactic scale or the supermassive black hole scale. But in history, we can see many fifth force experiment. The scalaron is also some kind of fifth force. But in lab, people did a lot of tests like equivalence principle violation.
Talk. The next lecture is by Olak Pratim Bordoloi of Tezpur University. Olak, could you please share your screen?
Yes, ma'am. Sure.
Okay. So he will be presenting a correlation study between far ultraviolet and infrared diffuse emissions from the dwarf galaxy Homburg 2. Please share your screen.
Ma'am, is it visible?
Yes. Could you please scroll to the next slide? Let us just check it quickly.
Yeah.
Yeah. Yeah. Right. Okay.
So good afternoon, everyone. So I am Ulaprodin Gordole from Department of Physics, Tezpur University. So today I'll be talking on the topic correlation study between far ultraviolet and infrared emissions from the dwarf galaxy Homburg 2. I have done this work under the supervision of Dr. Ubjuti Gogoi and in collaboration with Dr. P. Salima from Manipal and Dr. Margarita Safonova from Indian Institute of Astrophysics. So this is the outline of my talk. So firstly, let us have a brief introduction about what is interstellar dust, which is present in the interstellar medium. So the interstellar medium of a galaxy, contains a very large amount of material, nearly about several billions of solar masses, in mainly two forms, interstellar gas and the interstellar dust. But despite being present in such a huge amount, the presence of this interstellar medium, both the gas and the dust, is very less obvious because of their very low density. They are extremely rarefied. The density is around 10 to the power minus 21 kg per meter cube, which is very less than the best vacuums that we can obtain in the terrestrial laboratories, which is around 10 to the power minus 9 kg per meter cube density. So due to these extremely rarefied conditions, the presence of this interstellar matter is very less obvious. So if we talk about the contribution of the interstellar matter to the total mass of the galaxy, then about 10% of the interstellar gas contributes around 10% of the 10% to the total mass of the galaxy, whereas interstellar dust contributes only about 0.1% to the total mass of the galaxy. So this is in case of the Milky Way, and this is quite similar to the other galaxies also. So we can see that the contribution of dust to the total mass of the galaxy is very negligible. So this is the dust cycle. So dust is generally formed in the outer atmosphere of the late stage stars. So when the stars explodes via supernova, then this dust are released into the interstellar space, which are then again incorporated in some star forming nebula. Then from the star forming nebula, stars are formed. Then the star evolves through different phases. Then it again goes to the late stage. Then again the dust is formed in the outer atmospheres through the process of condensation. And then again via the supernova and other explosions, they are released into the interstellar space, and the process continues. The cycle continues like this. So as I've already mentioned that the contribution of dust is very negligible to the total mass of the galaxy, which is 0.1%, and also the fact that the interstellar medium is very rarefied. So that's why it is only in 1930 that the interstellar dust was first discovered by Trumpler. So, although being present in such a small amount, the interstellar dust plays a vital role in our view of the universe through a process called extinction that was first proposed by Trumpler in 1930. So this extinction occurs via two processes basically. One is absorption and other is the scattering. So dust particles, when radiation is incident on a dust particle, a part of the incident radiation is scattered by the dust particle, and the scattered radiation by the dust that is observed as the diffuse emission in the far ultraviolet wavelengths. So in addition to that, dust also absorbs the energy, that is radiation emitted by the stars in the short wavelengths, mainly in the optical and UV ultraviolet wavelengths, and they again irradiates it in the longer wavelengths, mainly in the mid-infrared and the far-infrared wavelength. So according to Bernstein, about 30% of the energy that is emitted by the stars as radiations, they are absorbed by the dust and they are again irradiated in the infrared wavelengths. So apart from controlling our view of the universe through extinction, dust also has some other roles in the universe. Basically, it controls the thermodynamics and chemistry of the gas. Also, it provides a site for the formation of the interstellar hydrogen molecule. So this is our objective of this work. So we wanted to study, the objective was to study the correlation between the far ultraviolet and the infrared diffuse emissions from the galaxy Homburg 2. That is our target galaxy. So why we wanted to do the correlation? Wanted to see the correlation because this correlation between the far ultraviolet and the infrared wavelengths will enable us to determine the nature of the dust grains which are contributing to these diffuse emissions, and which will later will help us in the modeling of the diffuse scattering from the galaxy. So coming to the data acquisition, since we are doing a correlation study between far ultraviolet and the infrared wavelengths, so the far ultraviolet data, we have done the imaging observations of the galaxy Homburg 2, the FUV imaging observations, with the help of the Indian space satellite that is called AstroSat. These observations, the FUV imaging observations of the galaxy Homburg 2 was performed with the UV8 instrument, the ultraviolet imaging telescope instrument on board AstroSat in 8 different epochs from 2016 to 2020. The PI of these observations was Dr. Margarita Safonova from Indian Institute of Astrophysics in Bangalore, and these are some of the information about the source. These coordinates and the distance from Earth. It is around 3.39 megaparsec away, or 11 million light years away from the galaxy. So this is the image that we have obtained from our observations, the FUV image. So this is the UVID final co-edited image, and this image was taken on December 8, 2016. So I will explain how did we get the image, how did we process the image in a while. But let us first complete the data acquisition part. So regarding the infrared data, so we have obtained the post-basic calibrated data, PBCD data from Spitzer Space Telescope from the Spitzer Heritage Archive at 7 different wavelengths, 3.6, 4.5, 5.8, 8, 24, 70, and 160 microns. So we have taken the data in 7 different wavelengths. Now, after getting the data, we have to correct it for the stellar contamination. For the stellar correction for the stellar contamination, we have assumed that the 3.6 micron emission is completely stellar emission. So we assume that. Then that particular 3.6 micron image was scaled by different factors. These factors are given here: 0.596 for 4.5 micron image, 0.399 for 5.8 micron image, 0.232 for 8 micron image, and 0.032 for 24 micron image. So then these scaled images are subtracted from the original images. For example, the 3.6 micron image was scaled by a factor of 0.596 to get the scaled image for the 4.5 micron image. 4.5 micron. Then that scaled image was subtracted from the original 4.5 micron image to get the dust emission. So whenever we correct for the stellar contamination, we only get the dust emission in the maps. So these factors were taken from Hello et al. 2004. But we neglected the stellar contamination correction at 70 micron and 160 micron because the stellar contribution decreases very sharply with the increase into wavelength. So these are the IR dust maps that we have obtained. So the first one is the 3.6 micron, that is assumed to be completely stellar emission, and the other 6 maps, they are the stellar contamination corrected dust maps at different wavelengths. Okay, so I have told you that the FUV image that we have obtained. So we have done the FUV observations with the AstroSat. Then we have to process it. So for the UV data reduction, we have got the level 1 data or raw data from the Indian Space Science Data Center. Now that level 1 data has to be processed with a pipeline, and as the output of the pipeline, we will get the output products that is called the level 2 data, which can be used for different scientific purposes. So the pipeline that we have used for the reduction or for the processing of the UVIT level 1 data, that is called JUDE, Giant's Ultraviolet Data Explorer, which was developed by Professor Jayant Murthy from Indian Institute of Astrophysics in Bangalore. So this JUDE is a set of routines based on GDL, the GNU data language, for the processing of UVIT images. So this is a flowchart for the different processes that is involved in the reduction with the pipeline JUDE. So I'll explain this flowchart. So first we get the level 1 data, which is the raw data from Indian Space Science Data Center. Then after getting the data, we give this level 1 data as the input to the pipeline, and as the output we get the output data that is called the level 2 data. Now, while processing through Jude, the Jude can process the data, the level 1 data, in two modes. First is the automatic mode, and the second is the interactive mode. So in automatic mode, we just have to give the level 1 data as the input to the pipeline, and it will automatically process the data and give us the output products. That is some fixed images of the sky and some photon event list, which is the level 2 data. But the problem is when we process the data in the automatic mode, then many times it happens that the image registration fails. So the image registration basically is the correction for the spacecraft motion. So if the image is not properly registered, or if the correction for the spacecraft motion is not properly done, then there appears some trails in the images. Then these images cannot be used for any scientific purposes. So what we have to do, after processing to the automatic mode, we have to check the images for each of the orbits for the image registration, whether the image registration has been done properly and the PSF is within the acceptable limits or not. If the image registration is not proper, not good, then we have to again reprocess the image through the interactive mode or the manual mode. So in the interactive mode, we can play with different parameters. We can set different parameters to get the best image registration out of it and the best PSF that we can achieve. So if the image registration is properly done, and if the image is properly done, then we can achieve up to the spatial resolution of the VIT instrument that we can achieve up to around 1.2 to 1.6 arc second. So, so after the image registration is done properly, then we get the level 2 data, as I've already mentioned. That is, there's some fixed images and the photon event list. Now, these images then have to be calibrated astrometrically for the coordinate informations. So this astrometric calibrations, we have a set of routines inside Jude, but we can use some other softwares also, like IRF also we can use for astrometric calibration. Then after the astrometric calibration is done, then all the images, all the individual orbit images, then we have to co-edge, or we have to place them in a common reference frame and produce a single image. So that is the final image which can be used for different scientific purposes. So this image I have shown. So that actually is the final co-edited image from after going through all the processes. This is the final image that we have obtained, and this is from December 8, 2016. Now, after getting the data, the far ultraviolet and the infrared data, we went on to do the correlation study. Because dust scatters, the process of scattering and absorptions, they are likely to give the UV and IR correlations, which will enable us to determine the nature of the dust grains which are contributing to the diffuse emission. So for correlation, why we did the correlation study? Because the rank correlation is a very, very important tool, statistical tool, which actually implies or signifies the relation between two quantities. And the rank correlation coefficient, the value lies between -1 and +1. So if the rank correlation coefficient comes out with +1, then that implies that there is a perfect agreement between the two quantities that we are comparing. If the correlation coefficient comes out to be 0, then it signifies that the quantities are completely independent of one another. And if there is the correlation coefficient is -1, then that implies that there is a perfect disagreement, or one quantity is the reverse of the other. So regarding the methodology that we have adopted, so we have selected 50 different locations throughout the galaxy for our study. Then on these 50 locations, we have performed the aperture photometry on both the FUV processed image, the final coded image, and the corrected infrared images within a circular aperture of 5 arc second, so that we can get the intensity values for our observed locations. So the FUV fluxes are in the units of arcs per centimeter square per second per angstrom, whereas the infrared fluxes are in the units of Magazinski per steradian. And these fluxes then were used to calculate the correlation coefficient. So the correlation coefficient that we have used, that is known as the Spearman's rank correlation. So the formula for calculating the Spearman rank correlation is given by this. This rho is the Spearman rank correlation, 1 minus 6 sigma di square by n into n square minus 1. So this di, so basically what we have to do after getting the flux values, we have to FUV and infrared. So we have to rank these fluxes in order of their decreasing magnitude. That means the highest flux value will be ranked as number 1, and the lowest flux value will be ranked as number 50. Why 50? Because we have 50 different locations, so we have 50 different fluxes. That should be done for both FUV and infrared. Then we have to subtract. We have to find out the difference between the corresponding ranks. That means for the first location, we have to subtract. We have to find the difference between the ranks of FUV and the IR fluxes. And similarly, we have to go on for all the 50 locations. So we'll get 50 different DI. So this DI is the difference between the ranks. Then we have to square them up. Then at last, ultimately, we have to add them up, which will give us this factor, this parameter, summation DI squared. And n is the number of is the sample size. So in our case, we have 50 locations, so n will be 50. So so in this way, we can get the experiments. We can get the rank correlation coefficient. And there is one more parameter that is called the probability of the p-value. So this p-value actually tells us how likely the correlation is, whether the correlation actually exists or the correlation is due to any chance. This p-value lies between 0 and 1. If the value is very close to 0, then we can say that there is some actual correlation that exists between the two quantities. But when the value increases, if it approaches near 1, then we can say that the correlation, there is no actual correlation that exists. So the correlation is entirely due to any chance. So these are the results that we have obtained for our correlation study. So generally, in case of correlation coefficient, if the correlation coefficient is greater than 0.5, then we can say that there is some kind of correlation. But if the correlation coefficient comes out to be less than 0.5, then we cannot trust the correlation value. So we have presented here the FUV IR correlations for 6 different infrared wavelengths. So because 3.6 micron we have not considered we have considered as a stellar emission, so there is no dust component. We assume that. So we have so remaining 6 wavelengths we have find out the correlation. So from this table we can see that for 24 micron and 70 micron, the correlation is greater than 0.5. This correlation is better compared to the other wavelengths. So and the probability value is also very, very less. This is 0.001. So this means that there is some actual correlation that exists between FUV and 24 micron, as well as between FUV and 70 micron. So these are the correlation plots that we have plotted. So on the vertical axis, we have plotted the FUV fluxes, whereas on the horizontal axis, we have plotted the infrared fluxes. So the first plot is for 4.5 micron, FUV versus 4.5 micron. The second is for FUV versus 5.8 micron. The third is for FUV versus 8 micron. And this one, the top one's 24 FUV versus 24 micron. Then FUV versus 70 micron and FUV versus 160 micron. So you can see that from this correlation plots, we can see that the correlation we have the best correlation that we have obtained for 24 and 70 micron, which is also clear from the correlation coefficient also, because the values comes out to be greater than 0.5 for 24 and 70 micron. So to conclude, so we can say that we have obtained from our correlation study that the emission at 24 micron and 70 micron, these are better correlated to the FUV wavelengths, far ultraviolet, compared to the other infrared wavelengths. So this 24 micron, so we can say that the best correlation is for 24 and 70 micron. So that's 24 micron emission is basically attributed to the warm dust emissions, which are emitted by the very small grains. So these very small grains, when they are present in the vicinity of some hot regions like star-forming regions or hydrogen-2 regions, which will have a lot of young, massive hot stars which are emitting UV photons. So these UV photons, the dust particles will absorb these UV photons and they will get heated up, and again they will re-emit in the infrared wavelengths, mainly in the mid-infrared, according to the temperatures. So Zhu et al. Showed that this 24 micron emission is very tightly related. They have a linear correlation, linearly related to the 70 micron emission. So 70 micron emission also we can consider as a warm dust emission. In fact, this fact was used by Walter et al., who used 70 micron emission as the warm dust ratio. So we can say that the grains, the dust grains that are contributing to the diffuse emissions are basically the very small grains, which are being heated by the hot and young, massive UV emitting stars. Moreover, from this correlation table, if you look at the far ultraviolet and 8 micron correlation, we do not find a very good correlation for FUV and 8 micron. So this 8 micron emission, that is basically responsible for the emission by the polycyclic aromatic hydrocarbons, so which is a very interesting dust grain candidate. So from our correlation study, we can say that which indicates that the pi emission is not very strong in this galaxy. It is very, very weak, and this fact was further confirmed. This fact was previously confirmed by Walter et al. From their spectroscopic study from the Spitzer IR spectrum. They also confirmed a very weak feature of the pi emission. So from correlation study as well as from the spectroscopic study, so we can say that the pi emission in this galaxy is very, very weak. So this is possible because the pi and the cold dust, they coexist, they exist together. So it may be like it is likely that in such hot environments near the hydrogen 2 regions and the star forming regions, the pi molecules have been destroyed. So this is an RGB image of the galaxy, which was created using the FUV, NUV, and the 2 mass K-band image in blue, green, and red respectively. So with this, I conclude. So these are some of my references.
Thank you, Ulok. Since we are running behind time, there we can maybe take a quick question if there is any. Any questions for Ulok?
Roman, just a quick question if possible.
Yes, sure. Please go ahead.
Yeah, I'm sorry I missed out, Ulok. Nice talk, but you are not using Galax. I mean, would Galax be also useful for your disanalysis?
Yeah, Galax will also be useful, but we have seen that the resolution achieved by AstroSat is because the one interesting fact about this galaxy is that it contains an ultraluminous exosource. So we have compared the AstroSat images with the Galax images. The Galax could not resolve the ultraluminous exosource, whether the AstroSat can quite well resolve the ULF source. So that's why we have used the AstroSat data.
Okay, thanks.
Okay, let us then thank Ulok once again. Please unshare your screen.
Thank you, ma'am.
Yeah, our next speaker is Gargi Sen. Gargi, could you please share your screen?
Yes, ma'am.
Yeah, Gargi will be presenting a study of the standing shock in the accretion flow around Cation black hole.
Ma'am, my screen is visible?
Yes. Yes, so you have about 12 minutes to present so that we can have some time for interaction. Please start.
So first of all, I would like to thank the NEMA organizer to give me the opportunity to present my work. So I am working on the standing shock in the accretion flow around Kartab-Nat space-time in the collaboration with Professor Shantabrata Das and Professor Prasad Maiti. So what is accretion? Accretion is a process by which a compact object gravitationally accumulates the nearby matter. This is the artistic impression. Here, this is the accretion disk. So when the infalling matter contains some angular momentum or rotational energy, then it forms a disk-like structure. It is called the accretion disk. And this is the compact object and this is the companion star. So why accretion is necessary? The energy release because of the accretion of mass m is given by equation 1. Here, this is the gravitational constant, capital M and capital R is the mass of the accreting body and radius of the accreting body, and small m is the accreted mass. So if we consider the radius of the accreting body is 10 to the power 6 centimeter, mass is more or less solar mass, then the energy release because of the accretion will be 10 to the power 20 R per accreted gram. Again, if we calculate the nuclear fusion energy, we can see that it is 6 into 10 to the power 18 R per gram. So we can say that the nuclear fusion energy is more or less 120 times smaller than the energy due to accretion. So accretion is very necessary to produce the higher radiation. Now, what is Cation spacetime and Nat parameter? Taub in 1951 first proposed the Taub-Nat spacetime, and Newman and Tamburno again rediscovered it. It is a vacuum solution of the Einstein equation. Nat spacetime is produced by the dual mass or the gravitomagnetic charge or monopole, which is called the Nat parameter, and it is physically interpreted as a linear source of pure angular momentum or it is considered as a massless rotating rod. So when the space-time contain car parameter, nut parameter both, it is called the Kettian space-time. And previously we have shown that spin parameter and nut parameter affects oppositely on the size of the black hole shadow. As the spin parameter increases, the shadow will be decreased. But if the nut parameter increases, the shadow will also increase. We can also find the particle behavior around the Kettian space-time in Chakraborty Bhattacharya's description. Also, recently the Chakraborty's group published a paper to show that the existence of the gravitomagnetic monopole in NEMA-VII star. So there are various accretion model. One is the spherical accretion model, then the standard disk model. Another one is the two temperature disk model, advective dominated accretion flow, and another one is the two component advective flow. So here we are considering the two component advective flow. What is this? This is a schematic diagram of this model. It is the figure is taken from Chakraborty 1995 paper. So here two component means one is the Keplerian flow and another is the sub-Keplerian. So this Keplerian flow is sandwiched in between the sub-Keplerian disks. And in this throughout the flow, there is always a competition between centrifugal force and the gravitational force. So when the matter is at the outer edge and at the very near to the black hole, always the gravitational force wins. But in between some region, gravitational force and the centrifugal force will be comparable to each other. At that point, the flow will be momentarily halt where it will be comparable and the matter will be puffed up at that region. But this piling up can't be go forever. So after some time, there will be a sudden transition from the supersonic state to the subsonic state. And at that region, the density temperature will be very high. This is called the shock transition and this is called the post-shock region. So this post-shock, because of this post-shock region here, the density will be very high and temperature will be very high. So the soft photon means the low energy radiation which is coming from the Keplerian disk will interact with the hot electron and it will again radiate as a hard radiation or high energy radiation because of the inverse componentization. So we get high energy radiation because of the shock transition. Again, if we can see the QPO feature, so if the shock oscillates, then it will also explain the QPO-like feature. Also, outflow jet kind of thing can be described by this model. So, being motivated to this previous work, we want to study the standing shock in the relativistic accretion flow around Kettian black hole, and we want to see how the nut parameter and car parameter affects on it. Here, we use the general relativistic equation of state. So, a generic stationary axisymmetric space-time is given by equation 3. These are the metric component, and these are the event horizon condition. So, from this relation, we can see if the second term means root under 1 minus ak square plus n square. Here ak is the car parameter, n is the nut parameter. So if it is greater than 0, then we will get a finite value of event horizon. So it will give us the black hole case. But when depending on this value ak and n, if this term is less than 0, then we can't get a finite value of RH. So it will give us the naked singularity case. Here we'll be talking about only the black hole case. So as the space-time is axisymmetric and stationary, we will get two conserved quantity. One is the angular momentum and another one is the energy. And in our hand, there is two conservation equation. One is the energy momentum conservation equation and another one is the particle number conservation equation. Here we consider G, C, MBH, mass of the black hole, equal to 1. And in this unit system, the length, angular momentum and time is expressed as GMBH by C square, GMBH by C and GMBH by C cube respectively. This equation 6 is the conservation of momentum, or it is called the Euler equation. Equation 7, it is the mass conservation equation. And another one is the entropy generation equation, which is equation 9. After that, we consider an effective potential, which is proposed by Ding et al. In 2018, and this phi is given by equation 11. And this potential helps us to consider the higher value of spin parameter. So we can smoothly calculate all the features for the highly spinning black hole. So here, as we are considering the Katian black hole, so we can also consider the higher spin value as well as the NUT parameter. So at the equatorial plane, the potential around Katian black hole is given by equation 12. It is also given by Ringetel 2020. And to study the dynamics of the flow, we have the wind equation in our hand, and another one is the temperature gradient equation. In this equation 13, we see the functional form of the NR and DR is given by this. And we can see that at some radial coordinate, the DR will be 0, but our flow is smooth. So to maintain the smoothness of our flow, NR should be 0 at that point. So where DR equal to 0 and NR equal to 0, this point we are calling it the sonic point. And we can also calculate velocity and temperature at that point. Now here we want to show how the effective potential behaves in presence of car parameter and NUT parameter. So in figure A, here we fix the NUT parameter and we changes the car parameter. So black one is the higher value, means it is 0.07 car parameter, and blue one is the lower value, means 0.0 car parameter. And in figure B, here we fix the car parameter and changes the NUT parameter. Here also the black one denotes the higher value of NUT parameter and blue one denotes the lower value of NUT parameter. So we can say from these two figures that the potential behaves in the opposite manner because of the car parameter and NUT parameter. In this figure, we plotted the energy as a function of critical point. Here black color denotes the saddle type critical point, the blue color denotes the spiral type critical point, and the red one denotes the nodal type critical point. This is called because depending on the value of dVdr. So when the dVdr value contains two values which are opposite in sign but real, then it is called a nodal type critical point. When the both dVdr value contain same sign and real value, it is called the nodal type, and when the dVdr contains the imaginary value, it is called the spiral type. So in our case, we are only interested on the saddle type critical point. Here we can see another thing. When in this figure A, we fix the NUT parameter and changes the car parameter. So as we decrease the car parameter, we see that the spiral type critical point ceases to exist. But in the figure B, we see when we fix the car parameter and as we increase the NUT parameter, then the spiral type critical point disappears. This is the parameter space and the solution topology. Here we plotted the parameter space in the energy angular momentum plane, and we divided 4 regions. In this region O, we get only one critical point, which is called the outer critical point, and solution look like this. In region A and W, we get 2 critical points and look like this. And again in region I, we get only inner critical point and the solution look like this. Now we'll be talking about what is the condition of forming a shock. So to form a shock, the flow must contain multiple critical points. Then the entropy accretion rate at the inner critical point should be greater than the entropy accretion rate at the outer critical point. Then the Rankine-Hugoniot shock condition should be satisfied. This condition is the mass conservation, energy conservation, and another is the pressure balance equation. So here we see that in the A and W region, there are multiple critical points. But in region A, the entropy accretion rate at the inner critical point is higher than the entropy accretion rate at the outer critical point. And here, entropy accretion rate at the inner critical point is less than the outer critical point. So we can say there is a possibility of forming shock in the A-type region. So now it is a solution where the flow contains shock. So the flow is coming from the outer edge, and after passing this outer critical point, there is a certain transition. It is called the shock transition, where all the conditions satisfied, and again the flow. So there is a jump from supersonic to subsonic, and again the flow passes through the inner critical point, then enters into the black hole. So from this Mach number, we can see the jump in supersonic to the subsonic state, and this is the theta, dimensionless theta means temperature. Here the black solid line represent when the flow contains shock. So the shock solution always have the higher temperature. This is the density We can also see the density will be higher if the solution contains shock, and the red one solution. So shock solution is always preferable. Here we plotted the shock location along with the car parameter and nut parameter. So we see that in the both figure we plotted for different values of lambda, means angular momentum. And in the first figure we see as we increase the car parameter, the shock location goes in the outward direction. But in the figure B, we see that as we increase the nut parameter, the shock location always go inside to the black hole. So behavior is opposite because of the car parameter and nut parameter. But in the both case, as we fix the car parameter and nut parameter, then if we compare for different values of lambda, means angular momentum, then it always shows that as the lambda increases, the centrifugal force always increase and it pushes the shock in the outward direction. It is the maximum value of the nut parameter as a function of car parameter. So from this figure, we can say that if we consider a car parameter, then this will be the maximum value of nut parameter up to which we get the shock transition or the shock solution. Now this is the parameter space for shock in lambda E plane. Here also we compare for car parameter and nut parameter. So in the first figure, we the red one represent the lower value of car parameter and the green one represent the higher value of car parameter. For this case, the nut parameter is fixed. And in the figure B, we fix the car parameter and we changes the nut parameter. Here, red one represent the lower value of nut parameter and the green one represent the higher value of nut parameter. So from these two figures, we can say that the parameter space also shifted in opposite manner because of the car parameter and nut parameter. This is the surface density. Here we plotted the surface density, which is rho into h. H is the half thickness of the disk. And this dotted line represent when the flow does not contain shock. And the solid line represent when the flow contains shock. And this is the shock transition. And then the flow passes through these two critical points. And here the blue one represent for higher mass accretion rate. This is for 0.05 mass accretion rate into Eddington mass accretion rate, and it is for 0.01 into Eddington mass accretion rate. So we can see that we will get the higher surface density when the mass accretion rate will be high and it contains the shock. Here we plotted the luminosity. Here we considered the Beam-Stirling radiation and we plotted the luminosity because of the radiation. First, here we plotted for luminosity along with the car parameter, and here we plotted luminosity with nut parameter, and we plotted for various values of mass accretion rate. So we can also see as the angular momentum increases, then also we will get the higher value of luminosity. So in conclusion, we can say that we have seen the effective potential behaves in the opposite manner because of the nut parameter and car parameter, and we will also see on the effect on the spiral type critical point, and we see the shock goes in the opposite direction because of car parameter and nut parameter, and also we showed how the parameter space change in presence of the car parameter and nut parameter. Then we plotted the surface density, and it is greater always for the shock solution than the without shock solution, and we also plotted the luminosity, which is always higher for the shock solution, and the luminosity also behaves in the opposite manner because of the nut parameter and car parameter. So if we can collect some observational features, and then we can compare between that the effect is because of car parameter or nut parameter. So in this way we can distinguish this. Thank you.
Okay, thank you, Gargi, for the nice presentation. So, any quick comments or questions to Gargi? If not, then let us thank her again. Gargi, you can now unshare your screen.
Yes.
Okay, so now it is time for the special lecture. And we are delighted to welcome Professor Somak Rai Chaudhuri, the director of IUCA Pune, who will be speaking about the evolution of galaxies in small groups. Welcome, sir. Could you please share your screen?
Yeah, thank you, Munmun.
Okay.
Great to be here, and I'll just share my screen and see whether it works. Can you see my screen?
Yes.
Okay, just a minute. Okay. Right. Well, thank you very much for this invitation to be here. This moves, right? My slides move.
Sir, not yet.
Is it moving?
It is not moving.
It is not. Okay. So this always has a problem. Let me just not then do. I can share my the entire screen, and that might.
Yeah, on Google Meet, sometimes sharing the window only creates a problem. So sharing the entire screen should not be. It should not be a problem.
So let me see if I can do that. Then I close this. Does this work?
We can see the screen. Could you please go to the next one? Yeah, it is working, sir.
Works. Okay, good.
Yeah.
So let me. Okay, thanks very much.
Okay.
Okay, so this has been a wonderful meeting. This is a huge range of talks. Not many people have talked about clusters and groups, and I thought I'd choose this so that I could talk about the current work on evolution of galaxies. And this is a work that we've been doing with many years on with many collaborators. Some of them are listed here, and you will see their names pop up from time to time. Just to talk about the background, we know that there's a whole variety of galaxies, and galaxies interact with each other, and they exist in various systems because the galaxies form on the cosmic web. There are some amazing work that has been done now on simulating the dark matter network of the cosmic web and how galaxies form on them. And the most interesting thing is that the galaxies are on this whole network, on this hundreds of megaparsec scales. They form on filaments. They exist in a very different kinds of environments, because you can see that if you look at some of these halos, which are this is a dark matter simulation, so there are different sizes of halos in here, and in each of these halos a galaxy forms, and these filaments cross where clusters exist, and then there are small groups of galaxies on these filaments. That's the kind of idea we have now. But the interesting thing here is galaxies form on the filaments. What happens to them? And where do they grow up? We know where they form. We often see them as a full-grown adult, I mean, at the end of their lives. But very interesting is to chart how galaxies evolve. And we can see that galaxies exist in all these kinds of environments. If you look at these crossings of these filaments, that's where the galaxy clusters are, very rich clusters, and you can find thousands of galaxies in them. But if you look at most galaxies would be in small groups, like our galaxy, which is in a group of 2 plus small dwarfs. So they are in these systems. And in fact, what I would argue is that in these small groups, a lot of things are happening. A lot of the evolution of the galaxies happen in these small systems. By the time they end up in clusters, they are mostly formed, and also not much exciting things are happening in them. As you can see, galaxies merge, clusters merge, groups merge, the entire universe is very dynamic. This is from one of these new simulations, the illustrious TNG, which came after the Millennium simulation, to show how large clusters form by actually accreting small galaxies. And it's in these small groups, the galaxies themselves interact with each other far more than when they end up in these clusters. If you look at our view, how much of the view of these clusters has changed. ROSAT, we in the morning heard Dr. Senorita talk about the various different kinds of X-ray observatories and what they've told us about X-ray binaries, for example. Here, we learned, it's the same amount of things we've learned from, because the resolution changed of X-ray observatories from arc minutes to arc seconds to sub-arc second, that we learned a lot about the emission, the diffuse emission from clusters of galaxies. And we now know that clusters of galaxies, things that are like this, have a huge amount of X-ray emission. And it turns out that the mass of the gas, the baryonic gas that is emitting X-rays, is far more than the baryon mass of the galaxies themselves, the stars. So it is the dominant component of cluster of galaxies. And here is a good picture of the Coma cluster with low resolution ROSAT, and you can see that you can see substructure in the basic distribution of baryons, which shows you how the matter is distributed to some extent. Here's a small cluster that has actually gone through a group that has gone through the whole cluster and has probably donated a lot of its galaxies and gas, etc., to the cluster, etc. So from ROSAT, which is the early 90s, our view of these clusters began to change, and this is the state of the art now. As you know, the Perseus cluster from the Chandra X-ray Observatory's launch in 1999, and the research that has been done at the centers of clusters of galaxies show that there's quite a lot of stuff going on in the centers, in the gas that is there. In addition to the galaxies, you can see them in the optical on the right, which is an H-alpha image superposed on the X-ray gas that's there. And this is what I'm going to talk about, but in the context of small systems. Now, in clusters, what happens is that the gas that you're talking about, which is in the intergalactic space and is the dominant baryonic component, cools. It will cool because it is due to the dark matter halo of the cluster, which is 10 to the power 15 solar masses. If you just do a virial theorem calculation, you will know that the temperature of this gas will be 10 million degrees, and it will emit X-rays, and it will emit X-rays to thermal Bremsstrahlung, which goes as you know, n squared t to the power half. And as it emits X-rays through thermal Bremsstrahlung, it is going to cool, and the pressure will become lower. There will be a pressure gradient. The gas will flow inwards, and the density will increase towards the center. And as the density increases, Lx goes as n squared. So more radiation will happen, more gas will cool, etc. So this is supposed to be a process that cannot come into equilibrium in principle. And this is what, for a long time, was believed, that clusters will be very, very cool in the middle. And these are systems, these are called cooling flows. And in the end, where will that gas go? It will go into the central galaxy, which will grow and grow and grow from stars, etc. And you can see this. You can see, for example, in the centers of clusters, we look at the temperature as a function of radius. It just cool towards the middle. But this is a low resolution view. What happened, and you can then look at what is the fate of this gas that is cooling. Eventually, it's going to cool from 10 to the power 7 degrees to 10 to the power 3, 10 to the power 2 degrees, form molecular gas and form stars, right? And you can see things are happening like that, but it doesn't really get to forming stars. It gets to, some of it gets to 10 to the 5 degrees, 10 to the 4 degrees. Most of it does not form into stars. Otherwise, you'd have giant galaxies in the middle of a cluster that, we don't see them, right? And the answer to this came from the Chandra X Observatory and the XMM Newton Observatory when they went up, and they showed that actually there is a source of heating in the middle of clusters. We now know it as AGN feedback, buzzword that's everywhere. And we can see a lot of the energy that's coming out of the central engine of the central galaxy of the clusters. So what happens is that as the gas cools, falls into the galaxy, a lot of this gas, some of the gas can fall into the supermassive black hole that is in the middle of the galaxy at the center, and then it will emit jets and the AGN in the center, and we can study the jets in the radio, for example, and low frequency radio. I'll show you some great examples, and you can see these jets will transport quite a lot of the energy out, and that energy will be multiplied by the medium, the intergalactic medium in the cluster of galaxies. Okay, so that's the idea. So we have this loop of kind of feedback loop set up in the centers of clusters, cool core clusters, for example, where you find these radio galaxies that are active. So it turns out that this source of heating often cancels the cooling effect. And so, as Chandra and XMN discovered, about 50% of galaxy clusters do not have cool cores. They actually have quite a flat temperature profile, because now we can see them in high resolution. We don't have this kind of a resolution of in terms of the centers of the clusters anymore. And in the cool core clusters, like the Perseus cluster, for example, still there is quite a lot of heating going on in the centers, so that the gas doesn't drop to levels where star formation would start. So now the question is, and you can see this happening here. I mean, here's the center of the, if you zoom into the center of the Perseus cluster, it looks like this. You can find how this energy that is produced by the central AGN of the little galaxy, not little compared to the cluster itself, galaxy in the center, produces this magnified in many ways in the intergalactic medium through shocks, and in particular through these things called cavities, the ghost cavities, the cavities which are essentially the jets coming out of the central source, blows bubbles in the center, in the intergalactic medium. Here's on the right the greatest example we know, MS0735, in which the blue is the X-ray, Chandra X-ray emission, and the red is the radio, in this case VLA. I have a very good GMRT observation of this as well, in which you can see the jets coming out. These jets are hundreds of kiloparsecs long, and they actually create these cavities in the X-ray emitting gas in the cluster, and these cavities, these bubbles, then rise in the intergalactic medium and do mechanical work on the intergalactic medium and transfer more energy, and so it's magnified. We studied in X-rays, in the optical, and as you will see, infrared and UV. They all tell you what's happening.